Hi everyone, we are going to explain the surface plasmon resonance. Before entering into detail of how it works, a SPR technique, first we are going to explain the main concept of the physical phenomenon and how the signal that the equipment detects is generated. Now, a plasmon is the particle name for a plasma wave. It is important to denote that the plasma wave is a periodic electromagnetic wave, and as any other such as the light and sound wave can be described as a particle. In this sense, those plasma waves confined to the surface of a conducting material are called surface plasmons. When a polarized light is incident at the resonance angle to the surface of a metal, at this angle, the photons in the light beam have a momentum equal to the momentum of the surface plasmons. Due to the energy absorbed by plasmons, a change of the reflection angle is obtained. In other words, optical energy is coupled into the metal surface. With this diagram we can exemplify the concepts just mentioned, as it is depicted when the light is polarized and incident to the surface metal. Causes an excitation in the electrons, giving as result the surface plasmon resonance, or as is labeled in the diagram, surface plasmon polariton, the dotted waves. As we can see, the change in the reflection angle is what the equipment detects.
The instrument for superficial plasmon resonance is quite like a normal spectrophotometer. It is composed by a source of light that will emit the light beam, a monochromator that only let pass a specific wavelength, a beam splitter that is going to divide the beam in two, one as a reference and the other one to evaluate the sample. Before reaching the sample, the beam light must be polarized and then react with it, finishing encountering with the detector, usually a photodiode, that is going to send all the information to a lock in the amplifier that compares the reference beam with the one that interacts with the sample, cleaning the signal. The clean signal will be sent to a computer, plotting the results. The main difference in the equipment, compared to a normal spectrophotometer, is the sample device. It presents three parts: a prism, that must have a high refraction index, a dielectric medium, and the metal layer in which the sample is immobilized, usually gold or silver due to its high propagation constant. This device is inside a goniometer, that allows moving the sample and change the incidence angle of the beam light. The reflex angle will vary depending on the sample immobilized in the gold layer, characteristic that confers to SPR the ability to monitor binding events in real time. By creating a flow of one of the compounds in the metal layer, in which the other compound will be immobilized, is possible to monitor the interaction in vivo, without using markers. All the signals will be translated into a sensorogram, in which each step of the binding process can be identified. For this technique the incidence angle is quite important. Only at a specific angle, the major resonance and signal are going to be obtained.
The first application we are going to review is the surface plasmon resonance indirect immunoassay for detection of 17-beta-estradiol, which is present in very small quantities for detection in blood. On this study, a SPR immunosensor has been developed where estradiol BSA conjugate served as a ligand recognition element, and anti-estradiol antibody is high molecular weight interactant. Equal volumes of antibody and different concentration of estradiol were introduced over the estradiol BSA immobilized gold surface. In this graph we can see the SPR response for the interaction of immobilized estradiol BSA conjugate and the antibody in presence of free estradiol. The shift in resonance angle decreased, with an increase in the concentration of free estradiol in the solution in accordance with the indirect competitive inhibition, in which the estradiol in free solution inhibits the binding interaction of antibody with estradiol BSA conjugate. The sigmoidal calibration curve indicates the inhibition of the binding interaction between antibody and estradiol BSA conjugate, in presence of free estradiol. The inhibition depends linearly with the concentration of free estradiol mixed with its antibody. The biosensor revealed a linear detection range, corresponding to the interval between 85 and 15% inhibition with a lower detection limit of 1 picogram per milliliter. Bearing in mind that the normal range of estrogen in blood is 2 and 40 picograms per milliliter, this method proves to be suitable for the estradiol detection in blood. Another application corresponds to the fields of nanotechnology. The article is entitled as Understanding the Nanobiointeractions Using Real-Time Surface Plasmon Resonance Tool. The objective is to understand in real time the kinetics of proteins when binding to the surface of nanoparticles. Nanoparticles are important due to their applications in therapies as they are involved on the targeting of drugs to affected tissues. The methodology used by researchers to analyze kinetics of protein bindings to nanoparticles consist of synthesis of negatively charged polylactic coglycolic acid, PLGA, and positively charged chitosan oligosaccharide by solvent treatment. Then, the nanoparticle was characterized based in size, distribution and surface charge. And to finish, the protein interaction studies were carried out by using surface plasmon resonance, with a Barcore 3000 sensor chip, and the polylactic nanoparticles were mobilized into the sensor. The analytes used are bovine serum albumin and hen egg white lysozyme. These conforms the liquid phase, and were injected for an association time of 2 minutes in different concentrations. The results obtained indicate that there is a concentration-dependent bindings between polylactic acid particles and the protein analytes. Also, it is possible to observe that at higher concentration of protein, higher will be the binding to the nanoparticles as shown on figure B in purple for bovine serum and in figure D in yellow for white lysozyme. To finish, we would like to thank our professors, Judith, Carla and Oscar from our team conformed by Andres, Pedra, Victor and Vittorio.